Determining absolute age using half-lives. To determine the absolute age, an actual numbered age, geologists can use a variety of methods. One way that geologists do this measuring of absolute age is by measuring the presence of a radioactive element and its decay product. This method is known as radioactive dating and uses known half-lives to calculate an absolute age. Whenever we talk about half-life, the half-life is the time that it takes for a radioactive element called the parent to decay into a non-radioactive element called the daughter. And so by analyzing the percentage of these isotopes, we can use that to determine an absolute age. So what you want to focus on is you want to focus on the percent of parents versus daughters that are found within the rock. So what I'd like to do now is go ahead and actually explain how we go ahead and do this. Okay, so as I said, what we want to do is we want to take this rock and we want to focus on determining what percent of the radioactive element is present, and by doing this we're going to be able to use known half-lives, as you saw in the chart before, to actually determine the age of the rock and how many half-lives have actually passed. Okay, so what we're going to do, let's say that you have 100 atoms of a parent isotope. Okay, well, if you have just one, if you were to analyze a rock and notice that you have 100 atoms of this parent isotope, no half-lives have actually occurred. So that means the rock was actually just made. And so as you can see, zero half-lives have passed. And then from that you're able to determine that the age is, of course, current day. Okay, but whenever you start analyzing these rocks, what you're going to start to notice is you look at how many of the parent atoms do we have and how many of the daughter products do we have. So you notice that if you were to analyze this rock, you would see that if you had 50 atoms of a parent and 50 atoms of a daughter, you would notice that one half-life has passed. So as you can see, over time, you halve the amount of parents as you go along, but you always have to have the end result of starting out with the original. What you had was like 100. So as you can see, as you progress through time, you get less and less parents and more daughter products. Okay, so how do you do this? What you do is you're going to take this rock and you're going to analyze, what percent of parents do you actually have, and then you're going to use what is called the half-life decay curve to actually determine how many half-lives have actually passed. After you've determined how many half-lives have actually passed, you're going to actually take and multiply that by the known half-life of that actual element or that isotope. Okay, so here's a perfect example. Let's say that we go and take a sample of this basalt, and of course this basalt right now is brand new. But looking at the rock on the left there, you take a sample of this basalt. One element that we are actually specifically looking for is we are looking for the mineral zircon, because zircon has a lot of uranium-238 in it. Okay, and so whenever you start looking at this, that uranium-238 is the radioactive parent. So what they do is they grind this up and then they start to analyze and say, okay, what is the percent of uranium-238 as compared to the daughter product of lead-206? So again, whenever you start doing this, you're going to be analyzing what are the percentages of parents as compared to daughters. And so let's say that we had 100 isotopes in there, and you found a ratio of 50 isotopes of uranium-238 and 50 isotopes of lead-206. So in other words, what you do is you put this into an instrument called a mass spectrometer. What it does is it separates out and counts the number of parent isotopes and the number of daughter isotopes, and then it looks at the ratio. So as you can see right here, this is a 50-50 ratio. You have 50 parents, 50 daughters. That leads you to 50%. So what you would do is you would go along the left-hand side, you would go to 50%, and then you would actually notice that on that 50%, you have 50% of the parents, 50% of the daughters, 50 out of the total 100 is 50%. You go there, and you would notice that one actual half-life has actually passed. Okay, now going back to our formula, we're going to take that 1 times 4.5 billion, which you can see the half-life of uranium-238 is 4.5 billion years, and that gives you an age of 4.5 billion years old. And so that's how you actually go about it. Okay, so let's look at another example so that you can see ones that are like a little bit different. Okay, so what we're going to do is we're going to analyze this granitic rock, and we're going to notice that we have 375 isotopes of uranium-238. Our mass spectrometer also shows us that we have 125 isotopes of lead-206. So that 375 plus 125 is equal to 500. And now you take your number of parents and you divide by that, and you see that we have 75% of our parents actually left. So that's what you want to focus on, the 75%. Okay, now what you're going to do is you're now going to go to the actual half-life decay curve. You're going to say 75% of the parent. You're going to go down. You're going to see that 0.4 half-lives have passed. 0.4 times the half-life is equal to 1,800,000,000 years old. That is the absolute age of the rock. Okay, so what you do is you focus on the percent of parents as compared to the percent of daughters in there, and then you take that and multiply it by the number of half-lives, and this is how geologists determine the age of the rock. So hopefully you found this video useful in determining absolute age using half-lives.